We posted the link both in the general Slack chat as well as the specific channel for this session.
Can you hear me all right? Is it coming through? All right. Oh, thanks for the invitation and thanks for coming to the Buddy system. Realize this is a pretty vague title because I wasn't really sure exactly what I'd talk about when I submitted the abstract, but I think really what I hope to quickly explore here is the relationship between cloud formation and bulk chemistry and some of the things that can tell us about these systems, especially in the context of these companion systems. So what more can we say if we combine what we know about cloud formation behavior with information that we get from these companion systems? So there's kind of two big picture questions that we're getting at here. I'm not going to claim to answer these by the end of the talk, but I hope that this will help provide some new insights for how we might think about some of these systems. So the first is just this very old problem of how do we say something meaningful about the deep atmosphere based upon what we can actually see at the top of the atmosphere. And so this goes all the way back to early planetary science. What can we say about the bulk composition of Jupiter, for example, since we're only, even with probes or even with Juno, we're really only seeing in the top layers of these objects. And then the second one is, in the context of formation, what are the abundance patterns that are inherited by these companion worlds? There's already some good discussion of this in the coldest worlds session yesterday, thinking about the C to O ratio, for example. So I encourage you to have gone to that yesterday. Okay, so here we're going to focus on a couple of specific outcomes from a recent study. I'm going to have to go through this pretty quickly. And so if you want all the details, I encourage you to follow this link I think that'll take you to the ADS for the paper published earlier this year, led by Emily, which is exploring some of the relationships here that we have between cloud formation and things like the C to O ratio. So the first thing we want to explore here is how does the bulk chemistry actually affect the types of clouds that we can form in a substellar atmosphere. Specifically, going to look at the magnesium to silicon ratio and the silicate phase stability. And then the second outcome here that I'm going to explore is how does that cloud formation affect the observed abundances that we can actually retrieve, we can actually observe at the top of the atmosphere, so namely C to O ratio in these atmospheres. So I'm going to go into these in turn, starting with thinking about silicate cloud formation. Now, I don't have time to unpack all of this, but very, very quickly, this is the general picture of equilibrium condensate formation. In this approach, you get a cloud forming when it reaches its vapor pressure saturation. And the type of cloud that you can make depends on these two factors, really. Simplified, it's what's actually thermodynamically stable at those conditions, and what do you have to make the cloud out of? So do you have the conditions where that cloud is stable, and then do you have the ingredients to make that cloud? And so the idea here is you have this PT profile, and for each of these objects, and these are these condensation curves, and you get a cloud, a condensate forming where these profiles intersect the condensation curve. Now, why these particular clouds? We sort of inherited these clouds over the years. And the reason we use these clouds is because for a solar composition gas, if you model the chemistry at these pressures and temperatures, these are the condensates that are stable for a solar composition gas. You'll also notice here, I have a horizontal line drawn for the one bar, just to note that in the subsequent slides, if you see a plot like along the vertical profile of an atmosphere, I'm going to be looking at an isobar profile. So when we're looking at the thermodynamics, the thermochemistry, it's convenient just to look along the isobar profile to see what's happening as a function of temperature. Okay, so if we look at this, we can see as we cool down from a very high temperature, we have things like these magnesium silicates forming, thought to be very significant clouds that form in these atmospheres. Sorry, I want to make sure I let's get there. And we find that we are distributing the magnesium and the silicon into phosphorite or instatite. These are familiar to us if you're looking at these things. And the reason we get this particular combination of silicates is because magnesium outnumbers silicon in a solar composition gas. So you can sort of think about this in a sense as that we have an excess of magnesium, and so we get this stoichiometry controlling the types of clouds that we observe. We also find that this sort of requires some re-equilibration between the phosphorite phase and the instatite phase in order to maintain mass balance between magnesium and silicon in this system. So this is a plot showing where you are putting silicon as a function of temperature. I should have labeled this. This is all gas phase silicon out here, but then as the temperatures cool, you start distributing silicon into these different condensed phases. So this is what you might expect for a solar composition gas along the 1-bar profile. Now, what we found a few years back, we started looking at some retrieval results, and we found that what happens, we asked the question, what happens if we have a shortage of magnesium? And so we did some models on this. This is coming out of the work in Birmingham 2021. And we found that if we have a depletion of magnesium relative to silicon, that actually changes which silicates can actually form in these atmospheres. Now, in this scenario, we have an excess of silicon relative to magnesium, and there's a sense in which quartz, SiO2, serves as a sink for that excess silicon in this case. So we have changed the condensation sequence in terms of which silicate phases are stable. Here, if we have magnesium to silicon of just 0.6, we still do get phosphorite at very high temperatures, never all through at once. We have to obey the Gibbs phase rule. But here we end up with clouds that are dominated by instatite and quartz. So bulk chemical ratios will have a really big effect on the cloud phases that can form. What's stable, what ingredients are available. Okay, so to very quickly summarize, and one of the results from the recent paper Calamari et al. Was that we found that there's this cutoff point at about 0.9. So if you're greater than about 0.9, you can generally expect more phosphorite and instatite. But if you have a magnesium to silicon ratio of less than 0.9, your silicate clouds will tend to be dominated by instatite and quartz. And so on the left here, this is from the paper. We, on average, remove about 20% of the oxygen goes into these condensed phases, and you can see the thermochemical distribution of oxygen between these silicate phases as a function of the bulk magnesium to silicon ratio. Now, the question is, where does this magnesium to silicon ratio come from? Is it the same as the host star? Assuming that it is, what can we do with that? And so this is using a sample from Brewer. This is also, these gray points are what were used in the Calamari paper. And I've plotted a Gaia 100 parsec sample too, using the RVS results. And I drew a line here at that 0.9 cutoff. And just to show that this suggests that we have a lot of systems where we might tend to have more of the silicate, of the quartz phase or SiO2 phase showing up. But if we have magnesium-rich systems, that'll tend to form our sort of normal, quote unquote, phosphorate and instatite clouds. So if we are inheriting the chemistry in these companions, if the chemistry is the same as the host stars, that suggests a very, very wide range, a very diverse range of silicate phases or phase distributions in these clouds. Okay, so that's part one. Part two, see the color change there. So how is the C to O ratio affected by cloud formation? And so here too, this is a very commonly retrieved, commonly sought after value. And so, what is the observed C to O ratio? And it's sometimes helpful to write it like this because then you don't have to worry about quench effects. You're just adding up all of the carbon that you can see. You're adding up all of the oxygen that you can see. So our total carbon is methane plus CO plus CO2, and our oxygen is water plus monoxide plus CO2, 2 times CO2. And the key point here, of course, is that what we observe when we look at a C to O ratio in an upper atmosphere is not the bulk C to O ratio for these atmospheres, because they're relatively cool, and a lot of the oxygen, about 20% typically, we find, has been removed by condensation. And so very quickly here, this is, an equilibrium model showing, where we have these clouds forming, they are removing species from the vapor phase, and that includes oxygen. So we can calculate how much oxygen is removed if we know something about the abundances of the condensate forming elements. So this is effectively what we're seeing. If we look at what the C to O ratio is doing as a function of temperature along a 1-bar profile. Down deep in the atmosphere, we have what we're taking as the bulk C to O ratio. Then we have the silicate cloud formation, which is removing oxygen from the vapor phase. And we're left with what we can actually see at the top of the atmosphere, the observed C to O ratio. So effectively, what we want to do here is quantify this effect, right? And we can do this using companion systems and looking at the host star chemistry as informing what types of element abundance ratios might we expect in these companion worlds. Okay, so there's a lot going on in this slide, but the point here is if we are high enough in the atmosphere, it is safe to assume that the condensates have already condensed. Right? So if we go to low temperatures, we've already condensed out any of the condensate forming elements. And because we can make that assumption, even if we don't know exactly what phases have formed, we can still say something about how much oxygen has been removed, because any of these condensates are going to obey the stoichiometry of these oxides that are forming. So, for example, we can consider the removal of oxygen by each of these rock-forming elements or these oxide-forming elements, and we can mix and match them in a way to account for any condensate that might form. Now, I just want to highlight here, these are not actual chemical reactions. What we're doing here is bookkeeping. We want to have mass balance between the rock-forming metals and how much oxygen each of these metals is going to take out of the vapor phase, right? But we can add these up as long as we have mass balance, so we can make phosphorite, instantite, or quartz, and 0 MgO plus 1 SiO2 equals 1 SiO2. And when we do this, we find that most of the oxygen that is removed, which is about 20%, about 90% of that 20% is really just due to silicon and magnesium. So we can really focus on those particular elements when we're thinking about how much oxygen actually gets taken out. Okay, thanks. So this was the approach that was done in Calamari et al. 2024. So we took stellar chemical abundances from this Brewer sample, which included things like the magnesium to silicon, the magnesium abundance, the silicon abundance, et cetera. And then for a given set of elemental abundances, using this mass balance approach, we calculated how much oxygen would be removed in each of these scenarios. And that lets us predict the C to O ratio in the upper atmosphere, because we can calculate what is our initial C to O ratio and how much oxygen do we remove through cloud formation, and what is the C to O ratio that we're left with at the top of the atmosphere. And so this is the results here on the left, showing a relationship between the bulk C to O ratio and the observed C to O ratio. And so I'm going to just very quickly walk through how we did this. We take these abundances from the Brewer companion, from the Brewer sample, and for that set of abundances, we can calculate what would be the C to O ratio after we form these clouds. And you can see there's a really nice relationship. Essentially, what we're doing is quantifying how this widens as you go to very high C to O ratios. What this lets us do then is if we have an observed C to O ratio, we can actually say something meaningful, maybe about what the bulk C to O ratio is for that object. So even if we can't see the bulk C to O ratio directly, if we can say something about the cloud chemistry that's going on in these worlds, we might be able to say something about what is the bulk C to O ratio for that object. And I'm out of time, so I'll stop there with my conclusions. Thank you.
Can't use the microphone in this room, so we have to project. We have 3 minutes for questions.
So, there are, based on your talk, we decided there's a correlation between the observed state ratio with the formation of anti clouds. Like, you see the correlation.
Yes. We did find that the C to O ratio did depend on the Mg to Si ratio, and that has to do to stoichiometric effects with how much oxygen you're removing from the vapor phase. So short answer is yes. Well, that's more sensitive to the magnesium to silicon ratio, but yeah. Yes. Yeah. Oh, I'm sorry. I think we're out of time. Yeah, great question. I mean, yes, I still think it's important to remember that we still need to have chemical pathways to make these things. So it's still going to come down to what can we make, what's available to make it. Phosphorus is kind of a whole other thing. I think that'll be somewhat independent of some of these results. But yeah, there's still a lot of uncertainties there. Obviously, there might be that ammonium hydrogen phosphate cloud or something that's showing up middle temperatures, but Mark.
Mark Barley, in the water's condensation sequence, the iron doesn't talk to the silicon. Like on Earth, like there's almost never.
Yeah.
The iron's always, how much, if it was mixed up enough, the iron would talk.
Yeah. So the question is, can we have iron and silicates talking? In general, the short answer here is the oxygen fugacity is so much lower. It's just way less oxidizing compared to things like the Earth's mantle that even if they were re-equilibrating or in contact with another, in terms of equilibrium, we would not expect much in the way of phthalate, the iron, the corresponding iron silicate. So yeah, it's pretty hard to do for hydrogen dominated atmospheres, as far as we can tell.
Channon, one more time. So we have Selena Makathias, and she's going to talk about new young groundworks.